So it's my great pleasure to introduce our speaker for today, Filip Ilievski. Filip joined us here at ISI in 2019. He got his PhD from British University, did a lot of exciting work in NLP, specifically in entity resolution. So he had a lot of great ideas there. And since he's been at ISI, he's done tremendous work in common sense reasoning. So he's been part of our machine common sense project. He's thought about analogy, how we look at embodied common sense in the real world. He's made a lot of contributions to a toolkit we built here, the Knowledge Graph toolkit, which has made it very easy to do all of the transformations and manipulations of knowledge graphs we take for granted now that we have KGTK. And he's also been thinking about the reality of how AI influences the world, from the stories that we tell our children to the traffic patterns we see around us in LA. The body of work is great. And so this Filip will be heading off to a tenure track position very soon. And this is one of our last opportunities to hear about all the great work while he's still at ISI. So please give a really great welcome to Filip.
Thank you. All right, thanks, Jay, for the very nice introduction. So I will cover, I'll talk about my thoughts and my prior experience and my vision for building synergistic AI with common sense. So to start with, let me, when we think about the world in the future, so we think about the world in 2050, AI is becoming more and more prominent. These days, it's kind of hard to imagine that in 2050, AI will not be playing a big role. And so we're thinking about a lot of these applications where AI helps us. So AI navigates complex information for us, anticipates what the other agents will do, helps us develop good ideas, helps us in our household, and sort of we imagine AI being everywhere around us and working together with us and improving our lives. One of the reasons why we are not in 2050 yet is the lack of common sense. So this is a talk in 2020 at USC by Oren Etzioni, where he shows this example how a computer vision system detects a car in a pool of water. So this is not just a mistake. We all make mistakes once in a while, but this is a mistake that people would not make. And so we say, okay, AI has no common sense. And we've been seeing this in other cases as well. So this is us in 2021, asking GPT-2 to name something around the house that's often replaced or hardly ever replaced. And so it's maybe debatable whether some of these things are correct or incorrect. However, what is problematic here is that the system tells us that kind of the same things are often replaced or hardly ever replaced. So there is 90% overlap between the top 10, among the top 10 answers. And so just chronologically, this is July 2023. So, more and more people, I think, are talking about this lack of common sense and how this is really hindering us from building AI that we can trust. So we see Yann LeCun a few weeks back saying, well, we have models that perform very well on our benchmarks, but they make stupid mistakes. They have no common sense. They can't plan their answer, can't reason. So this is a serious mistake and a serious challenge that we are facing with AI today. And common sense has been there for many decades already. The problem of common sense, the challenge of embodying AI with common sense reasoning skills. Ernst Davis defines common sense as the common knowledge about the world that's possessed by every school child and the methods for making obvious inferences from this knowledge. Here in this definition, he talks basically about two things. One is that there is a body of knowledge that we somehow share and we assume to be shared among people. And the other one is that we use this knowledge then to make some inferences that are somehow obvious and also shared between people. And this knowledge, as John McCarthy, who wrote this essay in '59 on programs with common sense, he defines common sense knowledge as all of these things. So there are basic facts about the world, about the events, facts about knowledge and how that's obtained, facts about beliefs and desires, effects about material objects and their properties. So there are a lot of things that go into this body of knowledge that we somehow have been shared. And so one way to categorize this would be to say, well, we have common sense that's about intuitive physics. So this is not advanced physics sort of formulas, but this is really kind of how we understand the world. So we know that the elephant would not be able to pass through this door and the ball would, and so on. We have intuitive psychology, where we anticipate what the other agents want, desire, what is their goal, what is their motivation. And then we have a lot of common facts about the world around us. If we want to have AI that possesses common sense, we should be able to have the AI know all of these things, but also apply them when they matter. So being able to contextualize its knowledge, its common sense to specific situations. So this brings me to my research goal, which has been how to build AI agents with comprehensive common sense that are synergistic. And the word synergistic here means that these agents are able to work with people. So that's the ambition. Now, there are a few obstacles to synergistic AI that sort of stem from this lack of common sense. One is that we are not able to control today's AI's behavior in meaningful ways. So, sure, we can have ChatGPT and we can ask it questions, but it's very hard to actually steer this AI in meaningful ways. Part of this comes from the fact that the AI has been actually, the way in which it has been trained, it's somewhat intransparent and maybe somewhat arbitrary as well. The second challenge is that the AI does not adapt well to novel situations. So we can have training sets, we're going to train the AI, it's going to do very well, 90%, but then we go out, we apply it to something else, and then the performance is often much worse. And then the third problem is that it's relating to its explainability and ability to collaborate. So we often have systems that say, well, I think this is class 6, and that's fine. But if we really want to have AI that can work with people, it has to be able to explain its reasoning and have a way to collaborate, to interact with people. Okay, so I talked a lot about challenges. So let me summarize some of the directions that we've been taking to address this. To build an AI that will be responsible, that will be controllable, we've been working on building solid knowledge processes. So we spent some work on sort of knowledge engineering. As Jay said, we developed a toolkit, and then we also use this toolkit to try to understand how to actually build some of these knowledge processes. We also did some analysis of bias in AI and trying to understand how that impacts the model decisions. We did some work on organization and enrichment. So we worked on aggregating a lot of different knowledge resources out there under a common framework, and then connecting that to psychological axioms and enriching that with additional knowledge from crowdsourcing and so on. In the adaptive pillar, we often looked into knowledge transfer. So not only training the model on more data, but basically doing this in a way that somehow makes use of these knowledge processes. So here we worked on two main things. One is adaptation methods, and the other one is augmenting by a combination of structured resources, so knowledge graphs, and also language models. And then in terms of explainable and collaborative, we looked into ways to combine neural methods, which which are able to perform well on various tasks, with symbolic models that give us sort of this explainability. And so here we looked into some ideas, for example, fusing language models and knowledge graphs, or more recently we looked into state tracking and so on. So the general framework that I'm gonna be using in this talk is the following. So we have synergistic AI with common sense through these 4 pillars: so responsible, collaborative, explainable, and adaptive. We generally avoid using the benchmark specific training data under the assumption of, if we want to build AI that has common sense, it sort of defeating the purpose that we always expect to have benchmark with training data that we can use. So we want to have a model that we can train once and then take it out on different tasks. Those tasks include the following. So we've been working a lot on question answering and story modeling, story generation, and then more recently, interactive tasks, argumentation mining, argumentation for quality and fallacies, and then various multimodal tasks. So I'm going to cover a few of these in this talk. Precisely, I'll be actually talking about question answering and story modeling, and then also about logical fallacies. All right, so essentially, so in the rest of this talk, I'll spend most of the rest of this talk talking about two different instantiations. So how would these four pillars actually come into play for two tasks? So the first one would be question answering and story modeling. So here, one of the initial example we started with was the following. So we have a certain scene description. You know, we have a stage. There is a woman taking a seat at the piano, and then there are various possible continuations of this sequence. The right one being that she nervously sets her fingers on the keys. This requires us to make certain common sense inference by connecting the piano to the keys and making sure that we understand sort of the implications of somebody taking a seat at the piano. You know, they're most likely going to perform. People are nervous when they perform, and there is all of that. At the same time, you know, she's not in the crowd watching the dancers because she's about to perform, so she can't be in two places at the same time. And so there are a lot of sort of implicit reasoning steps that go into this. So how do we know? How does AI actually know this? And we were able to actually find a lot of these pieces of reasoning across different structured sources. So rather than going and looking at unstructured data, we looked into knowledge graphs. And so we looked into ConceptNet. We found that pianos have keys. We looked into WordNet. We found that pianos are played by pressing keys. We looked at Atomic, and then we learned sort of more causal connections, that in order to play a piano, you really have to be seated by it, be on a stage, reaching for the keys, and so on. There are strong feelings involved. We looked into visual genome, from which we extracted visual common sense reasoning, common sense knowledge. We looked into FrameNet, from which we extracted knowledge about the frames and the roles that relate to performing. So anyway, we collected all of these pieces of knowledge. Now the thing is, what do you actually do with this? And as a next step, we built this graph that we call the common sense knowledge graph that sort of combines these 7 sources into a single resource. And so we did some work in making sure that we can use them all at the same time using sort of state-of-the-art knowledge integration methods. And so after we did this is sort of what we ended up with. So we'll have, for a use case of dog and catching frisbee and throwing and so on, we know that dogs want to play, and catching frisbee is fun for dogs. And if somebody, if a person throws a frisbee, then somebody else has to catch the frisbee. So we have all of this sort of network of knowledge that we can use to perform reasoning. And so in one of the methods, what we did is we used this to generate questions. So here, in this case, this was the simplest method, and this was really what we started with. We thought, well, why don't we just take the graph and use the structure of the graph to generate a massive amount of questions just on a click of a button, to say, well, I'm gonna create this synthetic data to be able to train language models in a way that they would be trained anyways. But now this time with a controlled set of common sense knowledge that we want to inject in them. And so the procedure that goes into this is pretty much, it's very engineering heavy, but it uses the structure of the graph and then uses various sort of properties of this. After that, we're able to create around 1 million of these sort of simple questions, and then give those to the model sort of train the model to perform common sense reasoning. And so in this work, we did that, and then we created this sort of common sense language model that we could then take and apply to various tasks, including question answering, social question answering, physical question answering, natural language inference. So tasks that we could phrase as multiple choice question answering tasks. Right, so after doing this, and so as I mentioned, we did not use the training data for this task. So we kind of started by saying, well, we're just going to try to build a model that is informed by sort of external resources that we can manipulate. And so by doing this, we were able to get sort of constant performance improvement across different tasks, on some more than others. And so, that was sort of the first encouraging step in which we were able to see that taking this knowledge, taking this structured knowledge and injecting this into the models, even in the simplest way, actually brought some improvements. So after that, we actually went back and we tried to use this a little more. So we created this large resource with many structured knowledge triples. But we were only using that to create questions, and a lot of the structure was lost. So one thing that we try to do as a follow-up here is to derive different dimensions of common sense. So we, among the authors of this paper, we sort of sat down and we tried to derive, to see whether we can cluster the kinds of knowledge that we have in the graph into different categories. And so we came up with these 13 categories of common sense, which we call dimensions. And so those include things like temporal knowledge, spatial knowledge, motivational knowledge, the things that you would expect there to be there in a knowledge resource. And so we applied those dimensions then to essentially cluster our graph into different partitions. And so after doing this, we could just go back to our method and use this to study the connection between these different dimensions and different tasks. So we could see that over here, if you want to perform sort of more broad common sense reasoning across different categories, that's the first data set. We are able to get, almost best performance if we combine all the knowledge, but essentially using some subsets of the knowledge, we're performing much better than others. So the model would benefit the most from knowledge about utility of objects, and then it would benefit very little from knowledge about sort of lexical properties of words, which is kind of intuitive. In the other data set, which is about social question answering, so over there we saw that using temporal knowledge was the most beneficial for the model, and again, using things like lexical knowledge was the least beneficial. So this allowed us to actually have this controlled mechanism for injecting common sense in our models and then observing how that impacts the performance on different tasks. Now, one of the implications of this is that if we build a model that benefits more from certain kinds of knowledge, the assumption is that somehow relates to what the model knew or didn't know ahead of time. And so in this case, what we did, we kind of reverted the setup and said, well, if we take the original model and if we give these questions without pre-training, does it actually really perform worse on things like temporal and utility knowledge and quality, which are more beneficial, and does it perform really better on lexical knowledge, which we assume to be more trivial? And so this experiment shows that that's pretty much the case. So I said that we started with question answering, and so we were able to develop this model that was pretty straightforward, just taking a language model, training it as you would anyway, just in our case adding this controlled knowledge process to actually manipulate what you train the model with. So that worked reasonably well, but it was not that exciting and certainly not very explainable. So in follow-up work, what we did is we looked into procedural reasoning over stories. So we had these short stories of 5 sentences. And so here the task is given 2 versions of pretty much the same story. Can you say which of the 2 stories is plausible and which one is implausible? And then also for the one that you judge to be implausible, can you point out where is the conflict? And so here the conflict is characterized on a sentence level. So here the first story would be judged to be implausible because we have John and he went into the office and all of that, but then he left his notebook at home and then he began writing down notes. So this sort of implies a certain sort of implausible or unlikely scenario. So the system has to say, well, I think this story is implausible. This is the conflict, and then also track the states of the entities. So the reason why this is implausible is that the location of the notebook is not in the office, but it's actually at home. So we built a system that could actually do all of this sort of at the same time. And so the system that does this is based on these 3 objectives. So the system has to classify a story, is it plausible or not plausible, but then on a deeper level, it has to find we have this conflict detector that for each pair of sentences says, are these aligned or are these sort of contradictory in some sense? And then on an even sort of deeper or finer level, we have this attribute classifier that for each attribute, for each participant and each attribute, it tracks what is its value. So, we know that the notebook is at home, and we know that the book bag is open, and we know, maybe that the soup is cold, and so we're keeping track of all of these properties of the different participants. Right. So actually, we built this model. However, to be able to train this model, we created this synthetic procedure to get a lot of data from our graph. So in this work, we thought, well, we have this structured resource and we used it to generate questions. Can we use the same resource to actually build something more complex? So can we actually build stories that come from this graph? And I think the answer is not fully. I think it's actually very difficult to create stories just by using the graph that we had. But we were able to generate stories under certain, with a bit of sort of assumptions and some manual intervention. So we took the axioms from Gordon and Hobbes, the psychological axioms. And so what we did there is we defined different story types that were based on these axioms. One such story type would be about substitution. So let's say you have a story where you feel cold and then you don't have a blanket. Can you use a jacket instead? Things like that. So we were able to, just by following notes in the path, to create many stories. And so we took these axioms, we formalized stories based on them, and then we just essentially transcribe those into queries in our graph that allowed us to create stories and to create explanations for those stories. So here, we can create right. So the story generation would be, I'm at home and I want to warm up. There is no blanket. Can I use a jacket instead? So that comes from sort of, it can be traced back to the graph. The explanation is actually, I think there is a typo there. So the explanation would be that, jackets and blankets have the same property. They are kept around the same place and so on. So anyway, this was, what we did to generate a lot of data to be able to train this model. But we actually went, one of the challenges here is that we have these stories, but then we don't have the story, the states for the participants in this story. So to deal with that, we sort of built this methodology that was able to detect the story participant. So a given story, we know that there is a merchant, there is a soup, there is a microwave mentioned, and then we extracted their states. So anyway, this is we used language modeling for this to actually be able to get to annotate a lot of stories and to be able to to use that as a distance supervision training data. Right. So with this method, we were able to get with this method where we use this sort of compositional reasoning from participant states to conflicts to story plausibility classification. We're able to get better performance sort of on in-domain data, even if we don't do any of this augmentation with the additional stories. If we expand our stories with our graphs, so if we only take 5,000 of those, we're able to perform much better on a bunch of other out-of-domain tasks, both for story understanding and for question answering that sort of require these narratives. Here we were able to do this with much less, so we are only able to perform. We only required something in the range of a few thousand stories, whereas in the past method I said that we used something close to 1 million. Right, and then we looked into diversity, so using different kinds of stories, so using natural stories and synthetic stories together, we were able to get much better sort of adaptivity and generalization. And so here is one example of why this works well. So this goes into the goal of adaptivity. So if we have an in-domain task, we have a baseline model that is able to perform. A baseline model that's able to perform very well on in-domain task. Our model does so and so. If we take an out-of-domain task, we take that same in-domain model and we see that it's actually it's not able to generalize as well to sort of new objects and new states, whereas our model is kind of performing on par. And so the reason here is that our model does not make as many assumptions on the in-domain data. So we use this external generation process that allows us to do better, but also we use this compositional modeling of different objectives. Okay, so to summarize this first longish part, for the tasks of question answering and story understanding, we built these methods that are responsible because we use common sense knowledge organization. So our training processes are based on structures that we can control and manipulate. They are adaptive because we use through the mechanisms of using data augmentation based on this knowledge. They're collaborative because we are able to model situations and sort of have them in a way that will be sort of approachable and understandable by humans. And then we have explainability through using these shared representations. So obviously this is not, none of these four aspects is perfect, but this is sort of the aspiration towards which we're building. All right, so I would like to talk about another instance of a task where we sort of try to do the same kind of pillars. So try to build models that are adaptive and generalizable and explainable and responsible, but for the task of identifying logical fallacies. So in this case, the task definition is something like this. So we have an argument. So in this case, the argument could be something like, well, there is definitely a link between depression and alcoholic drinks. I read this on Wikipedia. And then, is this a logical fallacy? Yes. And then the next two steps are asking the system to predict a given category. First, going to a coarse-grained category, saying, well, this is a defective induction fallacy, but then going to a fine-grained fallacy and saying, well, this is fallacy of credibility. So why is that? Because the source, there is sort of a reference to a certain source. And so here what we did in terms of sort of making this responsible is we aligned our work to sort of work done in psychology. So we studied how people have thought about logical fallacies in psychology. and we derive this taxonomy that we use sort of as basis for our work. So on a high level, we have these coarse-grained 4 categories: fallacy of relevance, presumption, ambiguity, and defective induction. And then we have a lot of fine-grained categories that fall under each of the coarse-grained classes. And then, so going further, we looked into ways to build an explainable model for fallacy detection. We built several. I will zoom in on one, which we kind of stuck with the longest. It's based on case-based reasoning, or specifically the idea of instance-based reasoning. So here the idea is that we want to explain why a certain fallacy belongs to a certain class by an example. So we're saying, well, this is a fallacy of credibility because this other fallacy that I have from query time, from my training data, is actually also a fallacy of credibility. In this case, so we took that, so the way in which the case-based reasoning method or instance-based reasoning method works here is that it has these 3 components. The first one retrieves similar examples from the training set. Then we have a way to adapt this example and the current example based on attention mechanisms. And then finally, we classify the current case by observing also the comparison to the prior one. And so one of the things we realized is that simply getting a case and finding another case that's similar on the surface was not good enough. So one thing we did here is we thought, well, can we somehow enrich the representation of the different of the input case and also all the training or exemplar cases, and try to connect them on some higher level. So as Jay mentioned, we've been working a lot on trying to figure out how to do this on a deeper level by sort of establishing analogies and establishing more higher order links. In this work, we went to halfway there by using a language model and asking it to analyze each of the arguments by providing the counter argument, providing the goals of the speaker, providing sort of like a general explanation, and also trying to extract the structure of an argument. The other thing that we did here is we built, to make sure that this is an adaptive system, we built a logical fallacy detection with curriculum learning. So the idea here is that we wanted to have the system first perform on simpler tasks and then slowly move towards tasks that were more complicated. So we first detect whether there is a fallacy, then we go to coarse detection of fallacies, then coarse classification, and then we go to fine-grained classification. We also tried sort of the reverse case where we start from fine-grained tasks and we move towards coarser-grained detection. Okay, so our results, as I mentioned, we tried different methods. So the instance-based reasoning method, which, as I mentioned, we spend most time with, this one performs optimally among the different methods, both on sort of, this is in-domain evaluation, and we also have out-of-domain evaluation. We developed several other methods that I'm not going into detail here, but they sort of have this injection of knowledge and prototypes, so different ideas. But we dive deepest into this one. Looking into the effect of curriculum learning, we saw that it helps adaptation for finer grained tasks. So this table goes from coarse to fine, and so you can see here that in the third sort of section, we're always able to do very well with this curriculum learning method. For coarse-grained classification, this is still mostly the case. And then if we want to do binary classification, we see that that this curriculum learning is sort of not helpful. I also mentioned that we did this sort of argument analytics where we take our fallacies, our arguments and fallacious arguments, and then we essentially enrich them with counter arguments, with explanations, goals, and things like this. We saw that overall this helps. We saw that counter arguments and deriving the structure was most helpful for the model. And then we were able to actually see, we didn't run sort of user studies in terms of explainability and until now, and so we only did qualitative analysis so far. But we can see that, for example, if we have an input sentence like, well, everybody is going to get the new smartphone, why aren't you? We see that we are able to get, the model is able to find cases that for the specific task of classifying fallacies belong to the same category. Or, if we have here faulty generalization, everyone knows that the teenagers are lazy. We get other things like, if we allow the housing development to be built, a resort will come next, and soon we won't be able any wilderness. So we have this sort of unpacking of more and more generalization, and so the model is able to connect those to some extent. All right, so in this work of logical fallacy classification, this is how we map these 4 pillars to what we did. So responsibility is achieved, or is pursued through domain modeling. So we try to align our methods by starting from sort of dominant classifications of logical fallacies in philosophy. We built adaptive systems by using curriculum learning, so trying to go from harder to simpler tasks most of the time. And then collaborative, because of argument analytics. So we took, we were able to get the arguments and then enrich them with additional insights that would open the space for collaboration. I think to be collaborative, we do need to have more interactive setup, but this is a first step. And then in terms of explainable, we derived this method that is able to explain by example based on the idea of case-based reasoning. Okay, so I'm gonna summarize and talk a bit about my vision and where I plan to go with all this. So far, I described 2 different tasks of question answering and story modeling, but then also logical fallacies. And I described methods that are, for responsibility, we looked into using common sense knowledge based processes and then domain modeling. For adaptive sort of methods, we looked into data augmentation and curriculum learning, collaborative through modeling of situations and this argument analytics, and then explainable through using shared representations and this instance-based reasoning or explanation by example. So these are just some instances of how one could pursue these 4 properties of a system. I think we're very far from claiming that we have achieved any of these 4 to a satisfactory extent, but these are sort of the things, some of the things we tried so far. Now, I think there is a lot to be done in taking these AI agents that we developed in the lab, which are, as I said, really imperfect. The numbers also show that, but also, we know that we should be able to do better. Anyway, so the idea would be to take these AI agents that we developed in the lab and try to see whether they'll be able to make an impact when teaming with humans. So I think there is a lot to be done there. I'm gonna talk about 3 different use cases that I'm personally interested in. There is one of the use cases is task-oriented dialogue AI. So we have been doing some work here in sort of taking this in the traffic domain, but I would be pretty interested to move towards sort of personalized medicine and therapy. I think there are interesting use cases here that relate to how we can take a sort of AI that we've been building and try to put it in application of people and to support some of these difficult challenges. Personalized medicine has grown. The need for personalized medicine has been growing a lot, and countries cannot really keep up with this. So I think there is a real need to have AI assist these use cases, and I think that AI with common sense reasoning skills is in a good position to do so. The other one is detection of malicious content, which is another super difficult challenge. So in this case, the use cases would be misinformation, hate speech. The work that we've been doing on logical fallacy and argument analytics, I think, relates to this use case. And so, connecting this to content moderators, but also to social scientists, and trying to see how we can take this AI, although imperfect, and try to connect this to these use cases and understand what are the remaining challenges, is, I think, an important sort of use case. And then the other one is ideation and discovery. So many domains here relating to journalism and criminology would sort of make use of AI that can have common sense reasoning skills. I think especially aspects like causality would be very important here. So analysts, journalists, I think there are various profiles that would be able to make use of such AI. So all of these are very difficult tasks. The reason why I actually singled out these three is because I think these are tasks that are both difficult for AI and for people right now, and pretty much actually impossible for either. And so I think there is a real need and opportunity to combine AI and humans. As a final slide, these are some of the technical challenges and needs for some of these use cases. So I think things like state tracking, prototype learning, causal inference would be interesting for the dialogue AI for medicine. Logical fallacies, theory of mind might be important sort of technical components of the AI for fighting malicious content. For ideation, things like analogical reasoning, planning, and so on would be also reasonable. So I'm not claiming that there is like a really one-to-one mapping between these use cases and the specific technical directions, but I think these are some illustrations of what I think can be done in each of these fields. All right. Well, thank you for listening, and thanks to pretty much all the collaborators that I have here. Hope I didn't forget anybody.
We can have questions in the room. Abel, are you? I guess we're not doing the Q&A, so I'm looking at the chat. If anyone has questions in the chat, I'll make sure to get some to you. Adam?
Can you hear me?
Yeah.
Hey, thanks. So let me start off first by, well, two things. First, I'm sorry that I'll have to work harder to work with you. But the second is, I think the work you're doing is incredibly important. So with that said, I want to challenge you on two what I think are assumptions, and maybe you know better than I do. The first is, and this is sort of being devil's advocate. The first is the assumption that we actually want AI with common sense. And here's why I say that. If you read the book by Duncan Watts, Everything is Obvious Once You Know the Answer, he points out how important common sense is for day-to-day existence in environments where things are pretty predictable and we have a sense of, what exactly is the right answer. But the minute you get to complexity, common sense fails us regularly and actually sometimes spectacularly. And so I would argue that assumption could come into conflict with like James Evans, who points out that in some of the use cases you're talking about, we actually want an alien intelligence that doesn't think anything like us, right? Because it will be anchored the way you are, these sorts of things. So let me challenge you first. We want common sense in AI. Here's a second assumption I'll challenge you on, is that we actually need explainable AI. If you look at, especially if people are going to use explainable AI. So look at the number of people who actually understand the algorithm that Google uses to return answers that people then will change their entire lives around, right? Itineraries are built based on information they get. They have no idea how the AI is actually working. How many people understand their cell phone or GPS? So I would challenge the assumption that we actually need this thing to be able to explain itself. And worse, by making it have to explain itself, we're actually constraining it from doing what it really can do, especially it's just a complexity. Over.
Thanks, Adam. Indeed, it's going to be more difficult. So, actually, I hope we get to talk before my departure anyway. I'm going to schedule a meeting and talk more. But I think both of these challenges are very, very interesting and sort of very suitable to discuss. I think the first one, my answer would be that we want to know, we want to be able to have the common sense reasoning ability. I think in some cases, as you say, we want to be able to maybe defy it and maybe go over it. In fact, one of the things we've been working on recently that I didn't cover, we worked on this on the idea of lateral thinking, or thinking outside of the box, where actually the goal is pretty much what prevents you from solving some things like that. I know that sounds like a toy task, but I think in a way the pretty much exactly what prevents you from answering a lateral thinking puzzle is the notion of common sense. So we make certain inferences that really put us in a box. And so we created this brain teaser task where we try to test this. And I think, my answer there would be that I fully agree with you that I don't think we always need to have common sense, but I think somehow we should be able to have that in our skill set. And maybe to also have the ability to turn it off when we want to. So there is that. The other one, the other comment was about, sorry, I forgot.
Explainable AI. Like, why do we need AI to be explainable when we're actually really bad at explaining ourselves? We can come up with stories, but we're very inaccurate about why we actually do what we do. And there's evidence that we are willing to use things that can't explain themselves if we have experience that it actually works well. And by making it explainable, we may actually dumb it down to the point that it actually can't do the amazing things that we want it to. Over.
Right. Yeah. So I think, from what I'm not, from what I understand from explainable and interpretable AI, first of all, I think these notions are pretty much overloaded. So I certainly should have said what I actually mean by explainable AI. I think I'm making the distinction between explainable and collaborative here, which sometimes I'm even struggling with. But I think explainable in this case would be sort of being able to understand what the system does. Let's say, so in the case of state tracking and story understanding that I showed, can you actually show why the system is saying something in the way that it is? I think the reason for this is because I think you are right that maybe as an end user, you don't always need to know what the system does. But somebody has to know in the pipeline, right? I mean, if you create an autonomous vehicle and if it's doesn't have this explainable, doesn't allow us to go and understand where it breaks and why. As a manufacturer, I think it will be very difficult to take it out there. If you're a company that produces medical equipment, I think just taking that out in the world without actually understanding where it breaks, I think would be probably not a good idea. So I think I'm going to it mostly from that perspective. I do agree that we shouldn't be super puristic about this and be like, oh yeah, everything has to be explainable to everybody and all of that. But I think certainly for some use cases we need to have the ability to understand what the system is, how the system is reasoning on some level.
Okay,
but I think that those are great challenges. I mean, I would love to discuss more.
Could you go back to your previous, your last slide? Yeah, that one there. I don't have a question. I just wanted to see it.
Okay. Linda had her hand raised. I don't know if on Zoom.
Thank you. Yeah, I have a background in communications, and it strikes me that and first, let me preface this with my first husband used to talk about AI in the 80s, and he worked for DEC in the 60s. So, this is a really interesting term, but it's been around for a long. Everybody's acting like it's not new. I heard about it in the 80s. But anyway, I'm from communications. I work for the state as a public information officer. And so from a communication point of view, this is fascinating in terms of two disparate brains with disparate references and experience in life and knowledge bases trying to communicate. And it seems most useful when there is a time constraint involved, because if you have all the time in the world, you can sit and talk to someone forever and finally get your idea across. But if you don't have time, if you have a serious time constraint, this is a wonderful application to try to understand, wrap your head around. So I hope I'm not offending anyone with my very simplistic reaction here, but I'm enjoying this immensely, I have to tell you. And I see an application. A friend of mine works for the Bureau of Prisons. She's an attorney. She couldn't be further in her background from the people she's working with than a giraffe and a turtle. And I'm just thinking, how do you communicate with these people? How do you communicate with them when you're supposed to serve a group of people and you have maybe no common points with those people, and you may have little time to communicate with them? I see this is like a wonderful application for AI. Just thought I'd throw that out there. And thank you so much for opening this to the public.
Thank you, Linda. I mean, thanks for your nice words. And we've been thinking about sort of tasks that require this human AI teaming, and we're not really the only one. There is many researchers working on this. I think that actually there are tasks for which we just don't know how to approach, and maybe coming up with ideas is one of them, or we all have ideas of ways of coming up with ideas, but it's not a very trivial process, and somehow defining that it's not easy. So but there are also tasks where indeed time is really a challenge. So we had this DARPA proposal on sort of medical emergency, and in many of those cases you really have to make a decision sort of in time, and sometimes you can't really wait for a day. So I think time is definitely one of the constraints. Or, resources could be another one. So different kinds of resources. So yeah, thanks for bringing that up. I think there are many. I think many of the use cases that relate to this would relate to time. Also including the one on medicine here, as you said. Like if we would have unlimited time and resources. Personalized medicine is perhaps not that difficult, but we just don't have that, and how to deal with this under constraints is a challenge. Yeah, so Adam said misinformation strikes me as a place where common sense would cause more trouble than not. Opinions on what's accurate, moral, right, or legally allowable are rarely well adjudicated by common sense. Yeah, I fully agree. I think this would be also another case where I don't think that the goal would be to just apply common sense and be very sort of righteous about it, and be like, okay, well, this is common sense, this is the right way. I think there is a path there where we could make this more relative, and it could be relative, let's say, to moral foundations. And so I don't think we should just go and make a certain stand. But I do think that being able to understand what role common sense plays in this is important. There are certainly many biases, but I think associating those biases to certain pieces of common sense knowledge is also sort of something that we should be able to do. And then on top of that, sort of being able to relate this to certain decisions. I think Adam is actually gone, but that would be sort of my response. Okay.
I don't see any more questions or hands on Zoom here. Okay, well, let's thank Filip again